Hello, I am Susobhan Ray, the Assistant Professor of SBST in EC Department. Now I am discussing uh, the module PN junction of solid state device. These are the outcomes I have discussed in this lecture: structure and principles of PN junction diodes and their operations of PN junction diodes, energy band diagram of PN junction diodes, and the basic operations of PN junction diode in forward and reverse mode. I also discussed the heterostructure, the Schottky junctions, and different IV characteristics plots of PN diode. And I also discussed about minority carrier concentrations, reverse recovery time, and diode current components in this lecture. First I want to discuss the basic structure and the operating principle of PN diode. So in this diagram we have seen that if you want to form a PN diode, you have to choose two kind of material. One is p-type material or p-type semiconductor bead, which is basically made by silicon or germanium. We are basically choosing silicon because their availability in market is better as compared to other semiconductor device. And another one is n-type material, which also made by silicon. And we assume that both beads or the total semiconductor device or the PN device is uniformly doped across the p-type and n-type bead. And here in this diagram we also seen that there are two terminal, one is anode and cathode of this normal PN junction device, and anode terminal is connected, anode and cathode terminals both are connected to external potential. That means we are applying some external potential across these two terminals. Here Na means the acceptor impurity, because p-type material is, but p-type bead is basically acceptor type beads. That is why the impurity which we have added, all of these are acceptor type impurities. And in case of n-type bead, it will be donor type of impurity, which is denoted by n suffix d, because n-type semiconductor bead basically donor type of semiconductor. That is why if you have to added some amount of impurity in this n-type semiconductor bead, it will be donor type impurity. Xn is nothing but it is the barrier width across the n-type bead, and Xp is denoted by the barrier width across the p-type bead. And Wn and Wp is the distance which should be moved by the carrier due to the migrations from P to N and N to P. Holes are basically moved towards the n-type bead, and that is denoted by Wn of P. And similarly electrons are migrating from N to P side, that is denoted by Wpn, width of the distance that should be moved by the electrons from N to P side. Now how does the PN junction basically formed? That is the question. If we fuse these two semiconductor material together, p-type and n-type, a junction will form. That junction is called the PN junctions. What kind of operation basically happen due to this formation of PN junction? We have to know, when n-type semiconductor and p-type semiconductor materials are first joined together or fused together, a very large density gradient exists between these both sides, P sides and N sides. As a result, electrons, after diffusion, electrons are migrating from N to P side. Similarly, holes are also migrating from P to N side, and due to these migrations of these charged particles, what will be happened? They leave some immobile ions across the junction, PN junctions. If electrons are moving from N to P side, then they will leave positive immobile ions. Similarly, when holes are moving from P to N side, they leave negative immobile ions across the junctions. As a result, the charge density of the P type along the junction is filled with negatively charged acceptor ions, which are basically denoted by Na, N suffix A, and the charge density of the N side along the junction becomes positive. This charge transfer of electrons and holes from N to P side and P to N side across the PN junction is basically known as diffusion technique. The width of these P and N layers basically depends on the doping concentrations. If the doping concentration is high, the width is smaller or the width is reduced. If the doping concentration is small or very low, then the width of the barrier is increased. This process continues back and forth until the number of electrons which have crossed the junction have a large enough electrical charge or repel or prevent any much more amount of charge carriers from crossing the junction, crossing over the junction. Eventually, when the equilibrium state, that means the neutral state, electrically neutral situations will occur, producing a potential barrier around the area of the junction. The donor atoms repel the holes, and the acceptor atoms repel the electrons. Since no free charge particles or charge carriers can rest in positions where there is a potential barrier, the region on either sides of PN junctions now become completely depleted of any more free carriers in comparison to N and P type materials further away from the junctions. And this layer around this junction, which have been formed due to these migrations, is basically called the depletion layer. Now I am going to the next slide. This is the diagram, or this is the descriptions about the energy band concept of PN homostructure or PN junction diode. Here in this diagram I have seen that this is the p-type bead. Suppose this one is the p-type bead and this one is the n-type bead. The depletion layer has been formed, and how does it form? I have been described in this previous slide. Here we have seen, in case of n-type bead, due to the migrations of electrons from n to p side, they leave some immobile ions which are basically positive immobile ions across the p-n junction. Similarly, in case of p-type bead, due to the migrations of holes from p to n side, they leave negative immobile ions across the p-n junctions. This red circle denoted the positive immobile ions, and this black circle denotes negative immobile ions. And the width of this layer is called the depletion layer width, which is denoted by Vd, and this region is denoted the depletion region. Now, in this diagram we have seen there are two components denoted by, basically there are two components which have denoted the particle or carrier density due to the movement or due to the migrations of charged particles from n to p and p to n side. We have seen that electrons diffuse from higher concentration to lower concentration region, and holes diffuse from higher to lower concentration region. In this case from p to n-type bead, and in case of electrons that will be n to p-type bead, because in n-type bead the majority carriers are electrons and minorities are some amount of holes, and in case of p-type beads the majorities are holes and the minorities are electrons. And due to this phenomena, what will be happened? A current will form from p to n side, and this current is basically called diffusion current or I diffusion. Now, what is basically happened when electrons moves over n to p region? I already told in previous slide they leave some immobile ions which are basically positive immobile ions denoted by red circle, and same things is happen for holes also. When holes are diffused from p to n side, they leave some negative immobile ions, and this movement or these migrations of charged particles forms a region which is called depletion region. Therefore, there in the region a built-in potential is formed, which is basically called the potential difference. And due to this potential difference from p to n side or n to p side, what will be happened? A current will generated from p to n side, which is basically flowing in the reverse directions of the diffusion current, and this current is called the drift current, and this drift current will flow from p to n side. Ideally, at equilibrium state, both the drift and diffusion current density, J diffusions from p to n or n to p, and drift from J diffusions means the diffusion current due to the migrations of charged particles, and which is flowing from one semiconductor to another semiconductor bead, one to other semiconductor bead, and at equilibrium conditions the J diffusions and J drift both are 0. That means if we take a derivative across the distance, respect to distance, if we take a derivative of electric field basically respect to distance x, then we'll get del of d of E by d of x is equal to 0, and del of E is nothing but it is basically the Fermi energy level in this semiconductor diode, and EF is basically independent of x if the derivative is 0. That means the Fermi level is constant. The Fermi level is constant. Here already I have added this diagram, or I have seen that in this diagram, the figure 1, figure 2a, the Fermi level is constant. That means the electric field derivative, Fermi level, Fermi energy or Fermi level energy, electric field derivative respect to x equal to 0. That means the diffusions and drift current, the summations of diffusions and drift current both are equal to 0 at equilibrium case. Now what is basically happen in figure 1 A diagram, I have seen this diagram basically represent the charge carrier's density. Charge carrier's density is nothing but it is basically depend upon the electric field, the rate of change of electric field with respect to distance, and this is basically denoted by del E del x, which is equal to rho of x by epsilon, which is the permittivity of the medium. Here in this diagram we have seen that these portions, this is the zero level, this is the zero axis, zero level, and we have get some amount of charge particles or charge carrier densities below zero level, and we also get some amount of charge particles or particles density above zero level. Why? Because here we have seen in this diagram, and I told earlier slide that when holes are migrating from P to N side, they leave some immobile sands which are basically negative immobile sands. Due to this negative immobile sands, I can conclude that the charge carrier or charge particles densities will be negative, and that is why it is denoted or drawn over here below the zero axis. This is the negative charge particle densities, and here when electrons are moving towards the P junctions, they leave some positive immobile ions, and due to this what will be happen, the positions of charge particles will be above the x is equal to 0 axis, and that is why it is denoted over here. Now the second diagram or B diagram, we have seen that electric field basically the integrations of rho x dx upon epsilon. So here what will be happened after integrations, these portions, this slope portions is negative because the charge particle densities over here is also negative. After that you are adding a positive to negative large number of rho or the charge particle densities, so negative number is falling down and this portions is going towards the 0, and these sections is basically denoted the positive half of this carrier densities rho. Now in case 3 or figure 3, we have seen that here the V of x is called the voltage across the distance x, which is basically equal to the integrations of electric field which is generated inside this region respect to distance. Here Vx is basically nothing but minus of integrations of Ex dx. So what we can conclude that when Vx is negative, integral of Ex dx, which is adding the area of E of x, which is also negative, so the potential Vx will be positive. Hence in this plot we have seen that it is increasing in upward direction. Now in figure 2, the second diagram, we have seen that the energy band diagram of p-n junction in equilibrium condition. Equilibrium means when we are not applied in external potential across the p or n terminal. Here in this case, before making contact, we have seen this is the p-type material and this one is the n-type material, and the Fermi energy, which is the intrinsic Fermi level, which is denoted by E of f of n. And in case of p-type material, the Fermi energy just above the Fermi energy denoted the Fermi energy, the positions of Fermi energy shown just over the valence band, because we already know that in case of p-type semiconductor bead we are added some acceptor kind of impurity. That is why the positions of Fermi energy level just above valence band. But in case of n-type, that will be opposite. So here we have seen that it is just below the conduction band, because in case of n-type materials we have added some amount of donut type of impurity. That is why it is called the donut type bead, and this is called the acceptor type bead. Q of chi is basically denote the electron affinity respect to the vacuum level. I will discuss later what is electron affinity. Okay. Now in this figure we have seen, after making the contact between P and N, in this diagram, energy band diagram, the n-type beads are basically filled up by plenty of electrons, because n-type means negative, and n-type beads, the majority particles are always electrons. Similarly, in case of p-type beads, there will be the holes, which is denoted by blue circles, and electrons are denoted by red circles. So after making contact, what is basically happened, electrons are moving from higher concentration to lower concentration region. That means n to p sides, I already told in previous slide, and holes are moving from p to n side, which is called the basically diffusion process or diffusion phenomena. And after these diffusions, the depletion layer has been formed, and diffusion currents is also flowing from n to p, because in inside semiconductor bead, after the migrations of electrons, they leave positive immobile ions, and in case of p-type bead, after the migrations of holes from p to n side, they leave some negative immobile ion across the junction. So we know that current or field will flow from positive to negative side. Hence the diffusion current will flow from the drift current will flow from positive to N side, which is denoted by I drift, and it is flow from N to P, because N side is positive immobile ion and P side is negative immobile ion. That is why we get diffusion current will flow from N to P side. This is the complete energy band diagram of PN junctions. Why it is called complete energy band diagram? So in this slide we have seen that after making contact we are getting this kind of energy band diagram. Now we know that the band bending structure is basically depend upon the potential energy, which is denoted by E is equal to minus E into V, which is denoted by minus E into V. E is basically denoted the charge of electrons and V is the net potential or voltage, external battery voltage or external polarity, whatever. V is basically external voltage and E is the total potential energy, which is denoted by minus E into V. So in this diagram we have seen when we are adding the potential energy, the band is going downwards bending and we are getting a constant Fermi level or Fermi energy, which is denoted by EF. Same phenomena is happening over here. Holes are diffused from P to N side and we are getting drift, and electrons are diffused from N to P side and we are getting drift current from N to P side. And due to these migrations we are getting this kind of band bending structure in PN junction. EC is nothing but it is the conduction energy, which denote the energy of conduction band. EF is nothing but the Fermi energy, and EI is nothing but the Fermi energy which has been occupied 50% of electrons over here. That is why it is called the intrinsic level. And EV is nothing but the energy of valence band, and X is the distance. Now this is the diagram after biasing. This is the diagram in equilibrium conditions, when just the band bending structure has been formed. Now if we biased the PN device or PN junction externally, this structure is for forward biased. That means P side or P terminal is connected to the positive polarity of the battery and N terminal is connected to the negative polarity of the battery. So what is basically happening? If we compare these two diagrams, we have seen that this portion or this level goes up, little bit up as compared to this. Why? Because I told earlier slide that the potential energy E is equal to minus E into V. Potential energy is equal to minus E into V, charge of electrons, negative particles, V applied potential across the terminal. So after migrations, what will be happened? I discussed earlier. Now here, due to apply this forward biased, what is basically happen? P terminal is positive, N terminal is negative. So what is happening over here? E is equal to minus E into V. That means here the V is negative. Why this level is shifted up or goes up? Because the potential energy is equal to minus E into V. If V is negative, that means if we multiply these two quantity, we are getting positive quantity. That means if the output of the potential energy is positive, then this level will be shifted up as compared to these equilibrium conditions. So what will be happened if this portion is shifted up? Actually, after forward biasing, a large number of holes and electrons produced to the junction, and they will recombine inside these junctions and a current will flow, which is called the forward current. So if we increase the potential or vary the external potential, we are getting much more amount of current up to a certain point, which is called the knee point. In case of silicon, that will be 0.6 or 0.7 electron volt. In case of germanium, it will be 0.2 or 0.3 electron volt. And after that point, we are getting a constant voltage, but we are a huge amount of current across the y-axis, and the sharp current, basically the current, that means the voltage become constant across the x-axis. If we have seen the IV characteristics curve, then we will get that the voltage has been constant across the x-axis, and this voltage may be 0.7, maybe 0.2 or 3, that is depend upon the material which you have been chosen, and this is called the knee voltage or the cut-in voltage, but the current increasing sharply. So when the level goes up, plenty of electrons are moving from N to P side, and holes are moving from P to N side or migrating from P to N side. And this is basically happened due to the attractions of opposite charge particles, because P side is connected to positive terminal of the battery, positive polarity of the battery, and N terminal is connected towards the negative polarity of the battery. And here, due to these reasons, what will be happened? The width of this depletion layer has been reduced. If we compare these two structure, we have seen that in case of equilibrium case, the width of the depletion layer is much more as compared to forward biased PN junction. But here the barrier has no discontinuity, because we have chosen this is a homo junction. Okay. In case of heterostructure, we will see how discontinuity helps and what is discontinuity, how does it form. But here we are not getting any discontinuity, so we are not getting large amount of current to change small amount of potential externally. So now, in case of this is just a normal forward biased PN junction diode. So now, if we increase the external potential again, what will be happened? This level again goes up, and a certain time will come when we are getting a straight line, but not any band bending structure. So what will be happen in that case? Plenty of electrons will flows towards the p-type bead and overcome the barrier or junctions, and this is basically called the junction breakdown towards the P. Here the volume is large, but carrier density is not large because there is no barrier discontinuity. Because here in these regions we are not getting any huge amount of charged particles. That means, in simple logic, as there is no discontinuity in barrier, carrier does not confined. Huge amount of carrier does not confined. Now, in case of reverse biased p-n junction diode, what will be happened? Reverse bias means p-type material is connected to the negative polarity of the battery and n-type material is connected to the positive polarity of the battery. So now what will be happened when the p-n junction goes to reverse biased? The level will be shifted down. If we compare this diagram with this diagram, we can see that here the level is shifted up, the slope is reduced, the slope height is reduced. That is why the slope height is reduced. But in this case we can see the level is shifted down, moving down, and the slope height is increased. So what will be happened? Here is a plenty of electrons in n-type bead and here is a plenty of holes in p-type bead. But due to this barrier height and due to this increase the width of the depletion layer, plenty of electrons are not able to moving or going towards the p-type bead. That means the width of the depletion layer and as well as the height of the depletion barrier is increased, slope is increased. That means we are getting small amount of current because the charged particles are not able to crossing over here from this side to this side, and hence the barrier potential is also increased. We have seen that this is denoted by electric charge V0 plus VR. VR is nothing but the reverse biased diode connection, reverse voltage which is given across the diode. Now a question has come, why this level is shifted down? Because I already told that potential energy E is equal to minus E into V. That means when V is positive, when the V is positive connected to the positive side, the positive polarity is connected to the negative side, that means V is positive. So if we multiply these two quantity plus minus minus, that means the potential energy will be in minus value. So what will be happened? This level will be shifted downwards. That is why it is called the reverse biased junctions, and hence what will be happened? The barrier potential is increased, the slope is increased, and the width of the layer is also increased as compared to this previous one. Here the width is very small if we compare these two structure. Okay, if we compare this structure, here width is much more, the width of the depletion layer is much more as compared to this one. Okay, so we are getting small amount of current in reverse biased situations. If we increase the voltage, we are getting a constant current. After some point, when the junction breakdown is happened, which is basically called the Zener breakdown, then we are getting sharp current, which is like this. This is called the reverse saturation current. Here almost the voltage and current, here almost the current is proportional, but the voltage is increased rapidly. But after a certain point, we are getting a sharp current, and this current is basically called, this effect is basically called breakdown effect, and the voltage by which this effect is occurred is called breakdown voltage. Now we are going to heterostructure. So what is heterostructure and how does it differ from the homostructure? In case of homostructure, we have seen that we are used same kind of material, same kind of semiconductor material, and their band gap, which is Eg, is also same. But in case of heterostructure, we have chosen compound material. Like here in this diagram, we have chosen aluminum gallium arsenide, which is the first material. Another one is gallium arsenide, and the last one is same aluminum gallium arsenide for n-type bead. This one is for p-type bead, this one is for n-type bead, and this is the gallium arsenide, which is basically sandwiched in between two material, and these materials are aluminum gallium arsenides for p-type bead as well as the n-type bead. These are basically high band gap materials, which I have seen in this diagram. Here the band gap is much more as compared to this. This is very low band gap material. That means aluminum gallium arsenides for p-type and n-type beads, they are high band gap, but in active regions, suppose this is lightly doped p-type materials I have chosen, and here the gallium arsenide which have been used over here is a low band gap material. Now if we have taken a double heterostructure, which I have chosen over here, here what is basically happened inside this structure? Here I have chosen aluminum gallium arsenide, which is higher band gap material as compared to gallium arsenide. Gallium arsenide basically low band gap material, and the electron affinity is much more higher as compared to aluminum gallium arsenide. In case of gallium arsenide, the electron affinity is 4 electron volt. In case of gallium arsenide, the electron affinity 4 electron volt. But in case of aluminum gallium arsenide, which is basically 2.2 to 2.3 electron volt, thereabout. That is why gallium arsenide is sandwiching in between two materials, compound materials, aluminum gallium arsenides. Now if we applied an external potential, so what will be happen? This is the intrinsic level, active region. If we applied the external potential, what will be happened? Suppose P terminal is connected to positive, this is positive terminal and this one is negative terminal. So what will be happened, this level is again goes up due to potential energy equations. We are getting this kind of diagram. So now after forward biased, when the conduction band of n-type material goes up, when the conduction band of n-type material goes up, the electrons are poured into the lightly doped. Suppose this is lightly doped gallium arsenide p-type materials which has been made by p-type materials. So this kind of electrons are pouring into the lightly doped p-type material like a water from higher to lower potential. Hence the valence band EV is also move up because E is equal to minus E into V. V is negative, so minus into minus, output will be positive. That means this level is shifted up. Due to this barrier, we have seen, due to this barrier, we are getting some amount of discontinuity over here, over here, over here, over here. So when the discontinuity is occurred, the carrier confinement is also become large. That means after migrations of particles from N to lightly doped material P side and highly doped P to lightly doped material P side, we are getting huge amount of charged particles into this bucket in gallium arsenide or this active region. That means the particles density is increased as compared to homostructure. That is why we have chosen basically heterostructure as compared to homostructure. How does discontinuity helps? In confined carriers, discontinuity of barriers helps built in very large current density even if we change small current I through the device. So by passing a small current you can get very large current density. That means the output current or the operations is totally controlled by you. But in case of homostructure, this is not controlled by the operator. That is why we have chosen heterostructure basically as compared to homostructure, and the main reason is discontinuity. Discontinuity means large amount of discontinuity. How does it helps? Large amount of, when discontinuity occurs, large amount of charged particles or huge amount of charged particles are confined into this bucket. So the carrier density is huge. That means if we change the output voltage, small amount of voltage if we vary, we are getting large amount of current. That is the basic advantage of heterostructure as compared to homostructure. Now next is Schottky junction. Schottky junctions is a special kind of junctions which is made in between metal and semiconductor. Suppose this is the substrate I have chosen over here, p-type substrate, and the semiconductor bead is n-type, and the channel is highly doped, made by highly doped n-type material. And over this region, the surface region, I have used a materials which is made by silicon dioxide acts as an insulator, and over it we made a contact or made a terminal which is made by metal, and this is called the metal terminal. That means the total connection is made in between metal and semiconductor. But here in previous diagram we have seen there is a connection in between semiconductor and semiconductor. In case of homostructure, in case of heterostructure, all of this connection made in between semiconductor and semiconductor. That means here in these configurations we have not used any metal. We have not used any metal. But in case of Schottky junctions, we have been used metal in between substrate and insulator. These are the electrodes which are connected across the surface of the semiconductor material. This is the various IV characteristics plot I have explained over here. From this plot we have seen there are basically 4 kinds of plots has been drawn. The first one is A, which is denoted the normal PN diode forward characteristics. If we see the plot, we can conclude that if we increase the voltage V, after a certain point the voltage become constant. We are not getting any voltage, but the current is sharply increased and exponentially, which is called the forward voltage and forward current. This region is the forward region. But in this quadrant we have seen if we increase the potential, the current increase, but very small amount of current we are getting across this region, and this is called the basically reverse saturation current. But after a certain point, suppose this point, when we increase the voltage rapidly, we are getting a sharp current, and this is called basically the junction breakdown or Zener breakdown, and the voltage by which this breakdown is occurred is called Zener voltage. Schottky junctions is one kind of rectifying contact junctions. Here we can also see that after a certain point the voltage become constant and the current increase rapidly. And nearly ohmic contact, in case of nearly ohmic contact, but what is the difference in between Schottky and normal PN diode characteristics plot? The difference is the Schottky contact currents starts or moving current goes up little earlier as compared to PN diode characteristics curve. But in case of ohmic and in case of near ohmic, what is the basic difference? Ohmic means nothing but it is a linear plot, straight line from this quadrant to this quadrant. But in case of near ohmic contact, we have it is not exact a straight line. Here we are getting good flow of current in both direction, but it is not a straight line. And here the near ohmic curve is denoted by the C. Now I am describing the Schottky junction by using energy band diagram. Here in case A, I have seen this is the metal and this one is the N-type semiconductor before contact. Okay. So there are some parameters I have given over here. For example, psi of m, this is called the work functions of metal unit in electron volt. Similarly, in case of semiconductor, it will be psi of Si, phi of Si, which is called the work function of silicon. Now, chi of Si, which is called the electron affinity in silicon. Chi of Si, which is called electron affinity in silicon. I will discuss later what is electron affinity. And the barrier potential energy seen from the metal side equal to Q phi of B, this one, and it is nothing but the difference in between phi m, the metal work functions, and semiconductor work functions, Q psi of phi of Si. Now the built-in potential on the semiconductor side can be expressed as VVI. What is VVI? It is the built-in potential due to the migrations of charged particles, and that is nothing but the difference in between phi of B minus phi of D. Phi of B, this is the barrier potential, and this is the phi D. So this difference is basically called the barrier potential in semiconductor, VVI. Now, what is the difference in between two diagrams? In case A, this is 0 eV, that means there is no contact has been formed. So that is why this is all are flat diagram. There is no band bending is happening or happened. But in after contact, I have seen there is a band bending has been happened. Okay. So now we are going to the next slide for these descriptions. What is basically happened? In case of forward biased, this is the forward condition, this one is the reverse conditions. Same phenomena is happen. In case of forward biased, this portion is shifted up. In case of reverse biased, this portion is shifted down, because I already told potential energy E is equal to minus E into V. So this portion is shifted up as it is forward, and this portion is shifted down as it is reverse. In case of forward biased, what is happening? Plenty of electrons migrating, and due to higher potential, the energy band goes up. So in case of reverse biased, due to lack of electrons, lowered potential occurred, hence the band goes down, and here the band goes up as compared to this one. So plenty of electrons is in conduction band, and they can't pouring down or crossed over the barrier. In case of reverse biased, plenty of electrons are over there, but they are not able to jump or cross over the barrier from this side to this side, metal side. Therefore, the current will be restricted in case of reverse biased Schottky contact or Schottky junction. But more importantly, a new current will come, and which is called the tunneling current. Assume for the particular electrons of metal there is a vacant state. Suppose there is a vacant state or permissible state, energy state, but there is no allowed state over here. Then the electron A tunneling through the barrier, this is the barrier, the electron A tunneling through this barrier, tunneling through these barriers from N to P side, that means semiconductor side to metal side, and due to this tunneling a current will generated or a current will get, and this current is called tunneling current. But in case of forward biased, what is basically happened? as the level goes up, hence electrons are easily or try to pouring from this level to this metal side, and these electrons or these carriers are basically called hot carriers, and this process is called thermionic emissions, by which what will be happen, the electrons are pouring from this side to this side and the current, and we will get current, and this is called the thermionic emissions. Now in next slide I discussed the minority carrier concentrations of P and N junction. What is minority carriers? Basically, if we concentrate the normal PN diode, we have seen that in case of P-type bead, suppose this is P-type bead and this is N-type bead. In case of P-type beads, the minorities are electrons, and in case of N-type beads, the minorities are holes. Okay, before discussing this slide, I want to discuss electron affinity and work function. So what is work functions? Work function is nothing, it is denoted here by phi. In case of metal, this is phi of m. In case of semiconductor, this is phi of Si, silicon. The work functions is nothing, it is a minimum energy required to moving electrons from a material to a vacuum level. Vacuum level is nothing. In physics, the vacuum level refers to a energy of a free stationary electron, that is the outside of the metal. That means here the electron energy will be 0, and this is called the vacuum level. Electrons with 0 energy. So this is called the basic work functions. Now electron affinity is nothing but this is also the energy attained by the moving electron from vacuum to the bottom of the conduction band. Suppose this is the vacuum level over here. So from vacuum state to conduction state, how much energy will required to move an electron, then it is called electron affinity, which is denoted over here E of chi. Now next I am discussing the minority carrier concentrations of PN junction diode. Forward biased, if we doing a forward connection in a PN junction diode, then we will get, after forward biased, this is the minority carrier density respect to forward biased. We are getting that electrons are migrating from N to P side and P holes are migrating from P to N side. For P-type, majority carriers are holes under equilibrium conditions, which is denoted by P0. But in case of N-type bead, the electrons are majority, and that is denoted by NN0. P0 for P-type majority carriers, holes under equilibrium, and N0 for N-type semiconductor beads under equilibrium condition. Due to the forward biased, from the positive terminals, holes are repelling holes are repelling from P side, hence PP0 this amount are repelled from P terminal and they are entered into N terminals or N sides, and they are become minority carriers. After that, these holes PP0 are try to recombine with electrons in N side. So what will be happen? The concentrations of holes is very large at the junction. The concentrations of holes is very large across the junction, but when they are moved far away, suppose this is a distance which is denoted by x. Suppose this is a distance denoted by x. Okay. Now move far away from the junctions, their concentrations get reduced, which we have seen in this diagram, and this is exponentially reduced. Similarly, when electrons are moving towards the p-type bead from N side to p side, their concentrations is much more across the junctions, but when they are moving across the junctions from the junctions towards the bead of the material, then the plot is exponentially decayed or reduced exponentially. And this is basically the plots of minority carrier concentrations in forward biased mode. But in case of reverse biased, the majority carrier does not contribute any current. The current which I have getting due to the flowing of minority charge particles from P to N and N to P side. Okay. In case of p-type bead, the minorities are electrons. Similarly, in case of n-type beads, the minorities are holes. In case of p-type semiconductor bead, the electrons, and in case of n-type beads, the holes, they are repelled by the battery potential because p-type is connected to positive and n-type is connected to negative. So they are crossing the junction and they are forming loops from negative to positive and positive to negative terminal. Here in this previous diagram, Pn is denoted the minority carrier of n-type, which are basically holes. Similarly, Np is denoted the minority carriers of p-types, which are basically electron. Similarly, in case of reverse biased, Pn is nothing but the number of holes on n-type bead, and Np is nothing but the number of electrons in p-type bead. Next, we are going to reverse recovery time of PN diode. So, what is reverse recovery time? It is nothing but a time if you suddenly change the voltage from forward biased to reverse, you must get a situation what you have seen in steady state forward biased and steady state reverse biased, which does not happen instantly or very quickly, and that requires some amount of time, and that time is required to change from forward biased to reverse biased is called reverse recovery time. That means, in a simple line, suppose a diode is connected in forward biased mode. Now you want to change the polarity of the battery, that means the diode will be in reverse biased, but this is not happen instantly, but this is not happen in a very small amount of time changing, have to take some time or have to request some time to operate in reverse mode, and this time is basically called reverse recovery time. When we removing the excess minority carriers NP minus NP0, that means if we go to the previous slide, here you have seen this is the excess minority carriers in P side NP, this is the difference NP, this slope is NP and this is the ground slope is NP0. So the excess minority carriers in P side is NP minus NP0, that means the difference in between two NPs, NP and NP0. Similarly, in case of n-type bead, the excess minority carriers difference will be Pn minus Pn0. Okay, so when we removing the excess minority carriers NP minus NP0 and Pn minus Pn0, so that is coming into the open circuit or the equilibrium state. That means the diode does not conduct either in forward either in reverse. From that it is coming into the steady state reverse biased condition. So if you want to operate a diode in a steady state reverse biased condition, you have to remove these excess charge particles from P side as well as N side. Then the diode will conduct in a steady state reverse biased situations. But before operate these situations, the diode takes some time, and this time is called reverse recovery time. If you suddenly changed forward to reverse biased, steady state reverse does not happen instantly, what I told already, and that requires some amount of time to going to steady state reverse mode operations, and this is called reverse recovery time. Okay, so now I am describing this plot. Now during what is basically happened during the removing of excess charge particles from P to P side and as well as N side, the diode is in conducting state. That means the diode is in operated on state. But the excess minority carriers are very large. Until it has been removed from the P-type and N-type bead, the diode is in conducting state. Later it requires some amount of much more time, and which is called a steady state reverse bias state. Now after removing the excess carriers on N side, Pn minus Pn0, because of that you can get a large forward current which is denoted by IF. In this diagram I have seen, which is denoted by IF, which is nothing but Vf by R, forward voltage by resistance. At that time T1, the cut-in voltage durations of the diode, we are getting the cut-in voltage which is this point, this diagram, which is 0.6 or 0.7 for silicon and 0.3 for or 0.2 for germanium. That is very small because this is in forward biased case. So this is the difference which I have been shown over here, Pn minus Pn0. Now in second case, if the input voltage suddenly changed towards negative V axis, this is the negative V axis, This one is the positive V axis. Now the input voltage suddenly changes from towards the negative V axis at t equal to t1, t equal to t1, this duration. Then the first step is nothing but has to remove the excess carrier. This is the first step, which I told already. If you want to operate a diode in a reverse biased mode from forward biased state, you have to remove excess minority carrier at first. So this is denoted by this line. That means it is decayed exponentially. Okay. But it requires some times. During that time the diode conducts, but in reverse direction. The diode conducts but in reverse direction. This is the forward direction conduction current. This is the reverse direction conduction current, which is showing in this figure, which is basically the negative y directions in case of reverse. In case of forward, the current has been shown in positive y direction. Okay, and this is the negative current which is flowing from N side to P side. This is actually nothing but the time duration. This is the time durations during the removing of minority charge particles in a particular instant of time, is denoted by minus VR by R. Actually, the total time are divided in two portions, which is called the storage time, another one is transition time. Storage time is nothing but this is depend upon the excess minority carrier concentration. That means this is a time required. This is the time required, the removing of minority charge particles. Okay, and that is why it is called the storage time. This is nothing but a time during the removing of excess minority charge particles, and this required time is called storage time, calculated by minus VR by R. Next one is transition time. What is transition time? After open circuit condition, this is in storage time situations, the diode is in open circuit condition because the minority charge particles are removing from one side to another side, and that is why it comes into open circuit conditions at duration T2. At duration T2, T is equal to T2. Now I am going to transition time. So after open circuit conditions, the reverse biased has going to taking place from this time duration T2, and because of that one, to reach the steady state reverse biased had to take some time. This time is called the transition time. That the durations of this time is from T2 to T3. So when at T is equal to T1, before T is equal to T1, the diode is in steady state forward biased. I have seen already. T is equal to T1. After T is equal to T3, the diode operated in steady state reverse biased. So the time required for the diode from steady state forward to steady state reverse is nothing but a sum of two time, which are basically storage time and transition time, TS and TT. So the total reverse recovery time is equal to TRR is equal to TS storage time plus TT transition time. So this is the descriptions of reverse recovery time by using these plots in PN diode. Now I am discussing the diode current components, which is in my last slide. Here a plot has been given which is in between current densities and X. Current density is denoted by J and the distance is denoted by X, and the diode we have chosen over here is uniformly doped diode. That means the NP0 is equal to PN0. Both magnetic carrier concentrations are equal and their magnitudes are also equal. Similarly, same phenomenon is happening over here. Electrons are diffused from N to P side and holes are diffused from P to N side. So the diffusion current and Xn and Xp, this is the distance. When X is equal to Xn, first we take the IP diffusions. IP diffusion means suppose the holes are diffused from P to N side and it become minority after diffusions, and that is denoted by IP diffusions across the N-type semiconductor bit across the distance. Similarly, when electrons are diffused from N to P side, that is denoted by IN diffusions in P terminal, in P semiconductor, P-type semiconductor bit. Okay. Here y-axis basically represent the current and x-axis represent the distance, and this is the depletion region, and xn basically represent the depletion region in N side, and xp represent the depletion region across the P side. Now first we take IP diffusion when x is equal to xn. In that case, x is equal to xn, the quantity would be aq dp pn0 divided by lp. A is equal to nothing but the area, q is equal to charge, and dp is nothing but the coefficient. dp is nothing but the holes diffusion coefficient, and pn0 is the number of holes in N-type semiconductor and LP is the diffusion length, how much distance has been covered is denoted by LP. And this value would be 1, this quantity would be 1, and this is exponentially decay and reach to the zero axis when it will migrating over the N-type semiconductor bit. Actually, what is happening over here after diffusions from this point to this point, why it is exponentially decayed? Because when the distance is increasing x, the whole quantity decrease exponentially. Suppose this is point A and this one is point B. If we join this plot, it will be an exponential plot. Now in case of electrons, suppose this is x is equal to minus xp, that means electrons are diffused from N to P side, and after going to the certain distance, this is the maximum point. Here the concentration is much more higher as compared to this. Here the value would be suppose 1. So when the distance is increased gradually, same phenomena is happening over here. The plot is gradually decreasing in exponential order. here NP0 and PN0 both are equal, because the diodes are is uniformly doped. Okay, that is why the magnitude of these components are equal. Now we can say the number of electrons going into n side and recombine with excess holes. Number of electrons which are moving into the n side, they are recombines with excess holes, and these holes are nothing but these are the minority charge particles in n-type semiconductor bead. And after that, recombinations across the junctions on the depletion region, these electrons are migrating towards the p region. Then number of electrons getting injected is something looking like that, which is exponentially decayed, and this represents the electron current flow. This is the representations of electron current flow. Same phenomena is happen over here. Holes are recombines with minority electrons, which is denoted by this plot. And after that, what will be happened? They are injected from p to n side, and after going towards the certain distance x, the plot will become exponentially decayed. Same phenomena is copying over here. Now, in this operations of minority carrier distributions, we are getting two current components. One is recombined current, another one is injected current. The first component is called the recombined current. These are the recombined current, and the second component are called the injected current, which are injected from n to p and p to n. So the total current I total is equal to nothing but it is the diffusion current of electrons flow from n to p side, and the diffusion current of holes from p to n side. Xn is represent the IP diffusions. That means electrons holes are diffused from p to n side, that is denoted by x of n, because this is the n-type bead, and the distance covered into the n-type bead, distance x covered into the n-type bead. Similarly, the distance x covered into the p-type bead is represented by xp. That is why it is called electron diffusions. The total diffusion current, the total current will be the summation of holes current diffused from p to n and the electrons current diffused from n to p, which is denoted by these equations: aq dp pn0 by lp, diffusion length, plus ap dn np0. This is for electron current, divided by ln t to the power ev upon vt minus 1. This is the simple diode current equation. So from this characteristics card of diode current components, we have seen that there are basically two current components. One is recombined of electron current. It tells us the number of electrons flowing per unit time are actually recombined with the minority carriers and go to the p side, which is eventually contribute diffusion current on p side, which is denoted by IN diffusion, electron diffusion in p side. And similarly, the number of holes coming out from p to n side is denoted by IP diffusion. And another current is called the injection current. So what is exactly happening over here? The whole currents, the holes here would be exactly equal to the electrons current which is coming from negative to positive terminals. Both are equal because this is a uniformly doped material, uniformly doped PN junction diode. So the number of holes flowing in at this point would be equal to the number of holes required to recombine with injected electrons to the number of holes injected to the depletion region. At the junction, when Xn is equal to minus Xp, under this assumption there is no generations and recombinations of carriers. That means when Xn is equal to minus Xp, generation is equal to 0 and recombination is also equal to 0. So this is my lecture on PN junction diode. Thank you.